Hey everyone, let's have a look at how to do some vector equations of lines. So, example 14, part A. Find the vector equation of the line through 1, negative 1, 3, and parallel to the vector negative I plus 3j minus k. Alright, so what we want is an equation in the form of r equals a plus bt. A is the position vector of a point on this line. So we have a line that's passing through this point right now. All right, and this line, and that whatever line this is parallel to this one, right? So A in the equation is the position vector of a point on the line. So this is the point we're going to use. So R is going to equal, now remember that a position vector is the vector from the origin to the point, and since this is already it, we're just going to use that. So I like to write it in vertical format, so I'm going to do that. So that's A plus. Now, usually when we write these, we put the parameter before the vector. All right, let's just go with that. And B is the vector that's parallel to this line, which we've been told already. So it's this one here. So this is the vector is negative 1, 3, negative 1. All right, that's part A done. Now let's do part B. Find the vector equation of the line through the points A and B. Okay, so this time the line is passing through A and B. Let's just, for simplicity's sake, assume it's going from A to B. Alright, we're going to incorporate that very shortly. And let's just pick a point that it goes through. Let's just pick the point A. It doesn't really matter, because this line goes through both of those points, right? So we want R equals A plus BT. So A is the position vector of a point on this line. We have two, so let's just use A. 1, 0, negative 4 plus, now let's put the parameter before the vector. Now let's find this vector. So remember that B in the equation is the direction vector. So it's basically a vector that's parallel to the line whose equation we're trying to find. So using the information we have, we can find the vector from A to B, because that's going to be in the same direction of the line, right? So it's actually on the line, but it's also so that means it's also parallel to the line. Bit of a strange one, but remember that if we want to find the vector from A to B, we take away the vector A from the vector B, so we'll get negative 2 take 1, which is negative 3, 1 take 0, which is 1, and 1 take negative 4, which is positive 5. So that's what we put for our B in this equation. Okay, and let's move on to part C. Find the acute angle between these two lines. Okay, so if you have two vector equations, if you want to find the angle between the two lines, all right, you just need to use the direction vectors. Right, because we're only interested, if we know which direction the lines are going, well, we can use the dot product to find the angle between them. Okay, so those two that I've circled there. So let's redefine some vectors. So I'm going to let the direction vector in part A be my vector A here, and the direction vector from part B be my vector B here. And then we're going to use the dot product. So cos theta equals, okay, A dot B divided by magnitude of A times magnitude of B, which gives us, so A dot B, remember, multiply the I components, J components, K components, add them up. So we have 3 plus 3 minus 5 over, okay, and remember magnitude is the sum of the squares of all the components in each vector. So it's going to be 1 plus 9 plus 1 times the square root of 9 plus 1 plus 25 which ends up being 1 over root 11 times root 35. And let's calculate this. 1 over square root 11 times square root 35, which is 0.05. Let's round to 0.051 approximately. So that means theta, if we use arccos, is 3 sig figs. Let's go with 87.1 degrees. Okay, so that gives you a bit of an introduction to vector equations of a straight line. Let's have a look at example 15. So we have two lines with the vector equations r1 and r2. We want to show that the lines intersect and find the coordinates of the point of intersection. Okay, so we need to use this point here. If the value of the variables, two lines will intersect if the value of the variables is consistent in all three equations. So the variables we're talking about here are s and t, right? And this is how we go about it. So let's look at r1 and r2 separately and come up with some equations for s and t, right? So maybe I just do this. Okay, so if we separate x, y, and z components, right? We have, so for x, y, and z, x, y, and z, okay, so we're looking at these numbers here. So x for r1 is going to be 3 plus s, and x for r2 is going to be 6 plus 0, which is 6. Okay, get what I'm doing? And then y, we go 0 plus s times 1, which is just s, and then for r2, 2 plus 4t. And then for z, negative 1 plus s, and then we have 0 plus 8t, which is 8t. Okay, so now we want to solve for s and t. So hang on, we'll get these equations now. So let the x's equal each other. So 3 plus s equals 6. Okay, s equals 2 plus 4t. And then z, sorry. Negative 1 plus s equals 8t. Alright? So from this, we can label our three equations. Okay, so from 1, s equals to 3. And then from 2, if we sub in s equals 3, so when s equals 3, t equals, so it'll be 3, take away 2, divided by 4, negative, 1 quarter, just 1 quarter, and then 3, okay, so let's use our two values, negative 1, we're trying to see if negative 1 plus 3 equals 8 times a quarter, 2 equals 2, alright, so that means the variables, so they're consistent, they work for all three equations. The variables are consistent in all three equations. The two lines intersect. Okay? Now, the next thing we need to do is find the coordinates of the point of intersection. Okay, well, let's just use one of the equations. Let's use R1. Doesn't really matter because we know now they intersect, right? So R1 is 3, 0, negative 1 plus S 1, 1, 1. So the point of intersection would therefore be when S equals 3. So when S equals 3, R1 equals, maybe I just say point of intersection. Why does it keep doing that? That's right. Point of intersection is, so basically sub in 3 and work it out. So it'll be 3 plus 3, 6, 0 plus 3, 3, negative 1 plus 3 is 2. Alright, and this will work if we do a quick mental calculation. This should work for the next, the other line as well. So when t equals what? A quarter. So 6 plus 0 is 6. 2 plus a quarter of 4 is 1, is 2 plus 1, which is 3. Yep. And then 0 plus a quarter of 8, which is 2. Yep, so it works. Right, so there's our point of intersection. Okay, starting to get a little bit more difficult. Right, but that's how you approach a question using the vector equations of a line. Let's have a look at a vector application question. So example 16. The vector position vector of a boat, A, t hours after it leaves the harbor is given by R1. So boat A has a position vector or vector equation of R1, and then a second boat B is passing by near the harbor. Its position vector at time t is given by R2. Okay, so we have another vector equation of boat B. All right, and this tells us that both boats are traveling in straight lines. All right, because of these vector equations. All right, part A, how far are the two boats at the time the first boat leaves the harbor? All right, so let's think about what that means. So at the time the first boat leaves the harbor, well, we've been told t is the number of hours after it leaves the harbor. So as it leaves the harbor, it must be at t equals 0, right? So let's let t equal 0 and find out where the boats are when t equals 0. So at t equals 0, R1 equals, if we sub in 0, we just get 0, 0. So that's the position of boat 1 when t equals 0. Makes sense? And then R2, alright, so let's sub in t equals 0. Alright, so that basically means we'll have 50 and 5. Okay. And now, if we want the distance between them, alright, think about it. We have 2 points, R1 and R2 now. Okay, if we create a vector from R1 to R2 and we find the magnitude, that's the distance between them. So I'm going to do it this way. So basically magnitude of R1, R2. So let's create a resultant vector R1, R2. That's easy enough. So that's just going to be 50 and 5. And because we want to find the magnitude, oops, no. It's going to be, if I work it out a bit more, so to get our resultant vector, we take away vector R1 from vector R2, which is just 50 and 5, which is the root of 50 squared plus 5 squared, which is approximately equal to, let's get my calculator up. Right, we'll put that, we'll calculate that when my calculator loads. Okay, but that's the answer. How far is each boat traveling? Right? So I'm going to do it using our understanding of the relationship between distance, velocity, and displacement and velocity, right? So since we've been given, let's finish this first. So we want square root 50 squared plus 5 squared, 50.2. Now, the question hasn't actually told us, has it? The distance, like the units? Alright, well if it's boats and it's in hours, let's assume kilometers. Alright, so I'm just going to say approximately 50.2 kilometers. Alright, meters wouldn't make too much sense. No, neither would anything else really. Okay, how fast is each boat traveling? Anyway, where were we? Okay, so we've been given position vectors. If we want velocity, well, that's the derivative of the position, isn't it? So if we do R1, so if we derive the position vector R1, basically just treat, if we treat, the vector 30, 15 as our constant and t as our variable, if we differentiate it, we'll just get 30 and 15. And then if we do the same to R2, alright, our velocity vector is just going to be 10 and 10. Okay, now remember that speed is the absolute value of the velocity, so basically if we find the magnitude of each of these new vectors, that's going to tell us the speed of each boat. So speed of boat A would be root 30 squared plus 15 squared, and boat B would be 10 squared plus 10 squared, square root, and then let's work those out. So 33.5, and let's just go with kilometers per hour, and the other one 14.1 kilometers per hour. Okay, and that's how we do velocity. C. Are the boats in danger of colliding if one of the boats does not change course? Okay, so we have to use what we've just learned about whether two vectors are going to intersect using the vector equations. So let's set it up this way. Remember that two vectors will intersect if the variables are consistent in both vector equations. So basically, if we can get a t that works for both equations, then they're going to intersect, or these two boats are going to collide, right? So let's just set it up this way for this example. So R1 and R2. So let's have a look at vector R1. Our x component is going to be, well, x equals 30t, and our y component, we only have two components here, which makes it a lot easier, 15t. Now for R2, our x component is going to be 50 plus 10t, and our y component is going to be 5 plus 10t. Alright, now let's solve for t. So let's make the x components equal to each other. So 30 equals 30t equals 50 plus 10t. So we get 20t equals 50. T equals, or 50 on 20 is 5 on 2. Now let's let the y components equal each other. So 15t equals 5 plus 10t. So we'll get 5t equals 5. t equals 1. Okay, so let's have a think about what this means. All the way back, thinking back to example 15, the t values are not the same. So that means the variables or the parameters aren't consistent for both vector equations, which means that these two vectors or these two boats will not intersect. All right, so therefore the boats will not collide. All right, so that's an example of a bit more of an application question with vector equations.